Hello and welcome back to Calculus 3. This is section 12.9 on Lagrange multipliers to end the chapter 12. So this is another section where we optimize. Now this time around we are not looking for min-max point anywhere where it occurs. We are also going to have now a constraint, and then we will be looking for the maximum and minimum points along that constraint. Now, you can recognize the classrooms where I teach when you take a look at this bottle and you see this black line drawn on it. That's my mark on in every classroom where I teach Calculus 3, because this is what I use to explain what's happening with Lagrange multipliers and what's happening with the previous section, 12.8, where you guys had to optimize the shape. So what I'm going to do now is I'm going to, this is a spray bottle, right? Just a standard spray bottle. And what I have here is a 3D shape that I can completely explain, right? Describe using parametric equations, some equations that we can write together. Now, I don't really care what the equations are. What's important to me at this point is that whatever way I orient this object, there is going to be absolute maximum somewhere and absolute minimum somewhere, because this object is something that you can pick up in 3D. It's finite, right? So it must have minimum, must have maximum, right? Now, if you observe along this object, there is this black line which I drew, right? So on a side, and you can see that that line, right, goes up and down, around in elliptical fashion. So now if I orient this either way, the question that we are solving today is not what is the maximum point of the spray bottle, that was 12.8, that was previous, but what is the maximum point on the surface of the spray bottle, but along the black line, right? So we are introducing the constraint. So I'm still looking for min and a max, but now this black line represents the constraint, and that constraint is projected to the surface of the object by having some kind of a curve C in the domain, which goes up. So if you look at the graphic in the book, you see the domain in the xy plane, and you see some kind of wavy shape on top. It's very easy to portray that if you have a piece of cloth, and then you just do that, and there you go. So now what you see here, right, is that kind of shape, and you see that you have some kind of g of xy constraint, which is in the domain, and that gives you the line that is drawn on top of this shape. Now, some portion of that line will go uphill, and some portion will end up somewhere in a valley, and so on. So min and max will occur along that line. So now we are going to learn a method in which we are going to learn a method which will tell us where these min and max points are along G. So if I remove the red line, if I remove the constraint, then you are just working out what we did previous class, which is the min and the max of the entire shape. But if you add the constraint and use Lagrange multipliers, you are working on under constraint, so you are going to look for min and max along that line, along that constraint. And you see, this is very important for some of the manufacturing jobs, not working on the floor machining, but actually designing factories and designing things. There is a law that people are allowed to work just a certain amount of hours per day and so on. So that will be a constraint, right? If the worker is by law allowed to work, let's say, no more than 12 hours a day, then that's a constraint. And you are trying to maximize your production while having a constraint that each worker that is on the floor is allowed to work maximum of 10 hours. That can be mathematically expressed. And then a whole bunch of other constraints that you might have, the amount of, number of hours that machine can operate continuously before shutting it down for regular maintenance. Maybe you need to put some lube on it and whatever needs to be done. Maybe change bearings and so on, and then bring the machine back up and to run. So a whole bunch of constraints need to be considered as you are optimizing. And I don't care what you're optimizing, whether it's profit or production or minimizing cost, or it's always going to be some kind of a constraint that you have to observe. So in that light, Lagrange multipliers are actually what you will use most of the time as you are working out these mathematical concepts, calculations that you need. So to start off, Lagrange multipliers method, right? It's very simple. You are going to have a function which will be in 2 variables or 3 variables, whatever. So you are going to have some kind of f of xy. Later we'll do f of x, y, and z, and you can have any dimension. So this is going to be objective function. That means that you are looking at min and max. That this one is providing us with a surface or a shape, whatever it is. And then we have g of xy equals 0, which is constraint. And the method is to equal the gradients. So that's the Lagrange multiplier. This lambda is called, the lambda is called the Lagrange parameter, and we are going to be eliminating that parameter as we go. So now all we need to do is to work out. The lecture is over. That's it. Done. So all we need to do now is to calculate a whole bunch of stuff. So this is probably the most disproportionate lesson of your life, where you get everything written in 3 lines, and then each problem is like 7 pages. Let's see. So in the light of what we did last time, we are going to be solving the nonlinear systems of equations. And then again, depending on the amount of variables, you will be solving 3 by 3, 4 by 4, and upwards in terms of systems. You have the del f and del g. Those are the vectors. So they will always produce the number of equations equal to the amount of dimensions. And then you also have lambda, which is another variable. But luckily, you also have a function g, right? So that's an extra equation. So you will always have exactly enough equations to find the amount of variables. So let's take a look at one of the vanilla problems, I guess. So problem number 6, to just illustrate the whole procedure, we are looking to optimize xy squared. When I say optimize, we are looking for minimum and maximum along the surface of this function. So fxy is equal to xy squared. And then subject to unit circle. So x squared plus y squared equals to 1. So this is what we have for our for the problem. When you hit the word problems, your job is to figure out which equation is which, right? You will have to figure out what is your equation, or what is the objective and what is the constraint. So now what do we do? Well, the method says that we need del f to be equal to lambda del G. Okay, so what's del F? Del F is the vector of partial derivatives of the original function. So partial derivative with respect to x is y squared, and partial derivative in respect to y is 2xy. And that needs to be equal to lambda, and now I need del G. And del G is simply 2x and 2y, as you say. Now, I am going to actually, in this first introductory example, rewrite this as g of xy is equal to x squared plus y squared minus 1 equal to 0, to put it in a form which was given up there, right, in a definition. So you see that we are looking for implicit function, right? So everything is on the left, and then it's equal to 0. And then you just take partial derivatives of each. Now, obviously, you know, this in this case equals to 1. 1 can go on either side of the equation because it will be derivative of that is 0 no matter which side of the equation is on. But, you know, sometimes you might have the, you know, x's and y's on the right, and your job is to move everything to the left, make it equal to 0, and then go and work out your del G. So the del F and del G, those are the vectors of first partial derivatives. So to create these two vectors, all I did is I set the I figured out what the partial derivatives are for f and put that in the first. So first one is in respect to x, the second one is in respect to y, and I did the same thing for the constraint equation, looking at the green. Now, if you observe, you have the two vectors that need to be equal. Well, we know that the x components have to be equal and the y components have to be equal. Yes?
So how do you get, so I understand how you got 2xy because you just took the derivative of f x comma y. Then how do you get y squared again, sir?
The partial derivative of this in respect to x. Okay. Derivative of x is 1, right? So you just have a constant, y squared.
Okay.
So now we have the red equation. So that's the red equation where you equal the first component of the vector, and then you're going to have the blue equation after that, which is 2xy is equal to 2 lambda y. And then we also have the constraint equation. You can actually use, if you want, x squared plus y squared equals to 1. Whatever. There are no rules over here. You just need to solve this thing. So here's your nonlinear system that is to be solved. And in this nonlinear system, you guys are deciding which way you want to do stuff. Do you want elimination? Do you want substitution? Can you replace something so it's easier? The only thing we don't care about is the value of lambda. That's the only thing we don't care about, because all of the points at which min and max occur during this along this constraint, all of those points will be along will be x comma y. So all I need to do here is, when I solve the system, find all xy points, and then what I do? The highest z value is max, and the lowest z value is min. Very simple once you get it. But now we have to work our way through these three equations so that we can solve this. Now, the first order of business is to simplify this as much as possible without dividing variables left and right. You see, if you cancel y in a second equation, if you cancel y on both sides, then you are technically dividing both sides by y, and that implies that your y is not allowed to be 0. But is there anything that says that y is not allowed to be 0? Right? Y could be 0, in which case you are not allowed to divide it. So you are, maybe I should do this. So that's our system, and this system needs to be solved. I just told you that you are not allowed to cancel variables on each side, unless you are sure that those variables cannot be 0. For instance, if you are maximizing a volume of a box or minimizing surface area of the box, then clearly sides of that box cannot be 0, right? Because there will be no box. So in this case, right, when application calls for some kind of calculation like that, you know that your side, your x, your y, your z, cannot be 0, in which case you are allowed to cancel y's. So there is a double standard there, right? For these problems that are just mathematical gymnastics, right? So this was not connected to any application. You are not allowed to cancel those y's because y could be 0, and by canceling it, obviously you're stating it's not 0. So we can only cancel the 2. And pretty much that's it. That's the only thing we can simplify for now. Now, the rest of the problem is supposed to be, can I somehow eliminate as many as possible variables? And the first thing you should try, it doesn't work all the time, but it works in a great number of cases, is to eliminate lambda. You don't need lambda at all. So if you are able to solve for lambda in one equation and plug that into the other lambda, that would kill lambda, and then you will only have to worry about 2 equations. Now, if that makes matters worse, you abandon that and try something else. So what I'm going to do is, from the first equation, I'm going to write that lambda is equal to y squared over 2x. I didn't cancel anything. This is somewhat saying that x is not allowed to be 0, but I haven't canceled anything, and I will be plugging this into the second equation anyway. So let's see what we get. So when I plug this in the second equation, what I get is xy on the left is equal to, instead of lambda, I have my y squared over 2x, and then I have the y over here. Now, what I'm going to do is I'm going to multiply both sides by 2x. When I multiply both sides by 2x, well, that doesn't really do anything other than move 2x to the left. And now what I have is 2x squared y is equal to y cubed. I still have the second equation, x squared plus y squared is equal to 1. So now, as you can see, my system reduced down to 2 equations and 2 unknowns. This is still nonlinear system, right? And it's a nonlinear system of values. Now, I did tell you you're not supposed to cancel any of the variables. There is a way that you can actually cancel the variables, but then you also need to consider what if, you know, a variable is equal to 0 and you go from there. So we can explore that as well. But let's see what else we can do here. What happened? Good. So now from the top equation, when I move everything to the left, I have that 2x squared y minus y cubed is equal to 0. So this is a standard trick. When you are not allowed to cancel and divide, what you do is you put everything on the left and you factor. And then you set each factor equal to 0. See? From here, you will actually get that y equals to 0. It is the solution that you would lose if you canceled y's. And that is one of the dangers of these nonlinear systems and methods of solving. Let me just show one more time. Guys, if you just canceled one of the y's, like this, right? You canceled one of the y's. Then you are losing solution y equals 0. And if you lose a solution, well, obviously, that's bad. So the trick to not lose solutions is to actually move everything to the left. And now, when you factor y, you will get 2x squared minus y squared equals 0, from where you're getting two equations, y equal to 0 and 2x squared equals to y squared. Right? So these are the two equations that you would get as you do what we call zero product rule. Now, interesting things happen, right? You bring in the second equation, and in the second equation, if y is equal to 0, you get that x squared is equal to 1, from where x is equal to plus minus 1, giving you 1, 0 and negative 1, 0 as points to consider for min and max. Yes?
Wait, how did we just get that, like that last step?
From this equation, if y is equal to 0, right, then this is done, then all I have is that x squared is equals to 1, right? That's why I drew the yellow line there, pointing that maybe I should also draw another yellow line of me feeding y equals 0 there. Is this better? So
yeah.
as I feed y equals 0 here, that kills y, giving me x squared equals to 1. You square both sides, square root both sides, you get plus minus 1. So now we obtain the first 2 points that we will have to compute z values for. You compute that from f equation, right, from the objective equation. Now the second equation here, well, it should be obvious what we are going to do. We are going to plug that equation into the second equation here and solve for, let's do green. So there we go, plug in. And we are going to get that x squared plus 2x squared is equal to 1. So what I got there is that, right, this y squared. And this is what I said, now that the methods are different than, right, you are used to do substitution, use substitution or substitute in your algebra class, right, to solve for x and then you plug everything in. Well, over here you solve for y squared, right? Because this has y squared and this has y squared, so you swap it as a block, right? The y squared from here gets replaced by this y squared. So that's that y squared, right? That's 2x squared. So now to solve this, we have 3x squared equals to 1. X squared is equal to 1/3. And then when you take the square root of this, you get that your x's are plus minus square root of 3 over 3 when you rationalize, which gives you x values. Now, you want to calculate y values for these x values, and you can do that, obviously, when you plug x squared there to compute that your y squared is equal to 2/3, which gives you that y is equal to plus minus, and now you have square root of 2, so it's a square root of 6 over 3, right? Because it's a square root of, yeah, square root of 6 over 3 when you rationalize. Observe that x has plus minus, y has plus minus. How many points do I get there? 4. Plus with a plus, minus with a plus, plus with a minus, and minus with minus. That's 4 points. So I have to check 6 z values. The highest is the maximum value, the lowest z would be the minimum value. So now I have to consider root 3 over 3, root 6 over 3, root 3 over 3, negative root 6 over 3, negative root 3 over 3, root 6 over 3, and negative root 3 over 3, negative root 6 over 3. These guys are candidates for min-max. Please make sure that you actually end the problem. I had to circle it red over here just to, have them all 6 on a pile, but that's not the answer. The answer is I want to know which point is a max. So now you have 6 calculations to do, and you will be plugging these numbers in the f equation because z equals f of xy. So you go back to your objective equation, which is f equation, and plug these one at a time, right, to produce z values. So here, z value is equal to f of xy, which in our case was given as xy squared. So now, I will compute z of 1, 0. Z of 1, 0 is 0, giving me 0.100. Now I'm computing z of negative 1, 0. This is the second point on the list. This is also 0, giving me negative 1, 0, 0. So that's the first 2 points. Now we go to the next one, which is the root 3, root 6, right? So z of square root of 3 over 3, square root of 6 over 3, and that will be square root of 3 over 3 times square root of 6 over 3 squared. Now, we have root 3 over 3 times, and on the second one is, good effort, 6 over 9. When you square it, right, square will kill the root, and you have 6 on top. On the bottom, you have 3 times 3 is 9. Now, these will cancel, so we have 2 square root of 3 over 9. So what is the point? The point is root 3 over 3, root 6 over 3, and 2 root 3 over 9. Great, 3 to go, right? Now, if you observe, there will be symmetry here because y is squared. So if you have, always the same numbers coming in and just playing with signs, obviously that z of root 3 over 3 and negative root 6 over 3 is going to give you the same point on z, coordinate. So we have 2 root 3 over 9 on this one. And then the others are the same values except they have negative on x. Negative on y is getting squared, so it always dies. But negative on x survives because it's just a single x, right? So the other 2 points with negative root 3 over 3 and root 6 over 3 will give us negative root 3 over 3, positive root 6 over 3, and then this will be negative 2 root 3 over 9. And finally, z of negative root 3 over 3 and negative root 6 over 3. So you have to compute all 6 points. Negative root 3 over 3, negative root 6 over 3, and negative 2 root 3 over 9. And there you go. Now I'm trying to set, yep, there they are. So these are all 6 points that are computed. Sometimes you are going to end up with 2. Sometimes you're going to end up with, 16 points. You need to find your z values for all of those points. Once you have the z values, you use your eyes and you look at the thing and you figure out, right, which, no coughing, is the min and which is the max. So we have the max values, 2 of them, and 2 min values. And these zeros are in the middle and we don't care. Is it possible to have multiple values? Yeah. Right? if I have a sine function, and I go sine function from 0 to 10 pi, 0 to 10 pi, I have 5 max values, right? Because 0 to 10 pi is 5 periods of sine function. 5 periods of sine function means 5 max values and 5 min values. So I can have as many of these min and max values as I want in a single shot. So this is problem number 6 by nature, the shortest and the quickest to do, right? With the least amount of aggravation. And obviously this is done to illustrate the method. So let's go back and, yes?
Are they the absolute maximum or?
Yeah, it's absolute. Well, it's, look, it is the absolute maximum regarding the constraint. Because as you are looking at the black line on this spray bottle, yeah, it's the absolute maximum along that constraint, but there is a maximum here that it's actually absolute maximum because it's object that I can hold, right? So this would be the absolute maximum of this one, whatever. But then there is a maximum here with the constraint. So the answer to your question is yes and no, depending on your definition. So if you call it absolute maximum, it is definitely absolute maximum along the constraint. No questions asked. No questions asked. But as you can see, is it absolute max for the object? No, right? Because there was a higher point. Let's recap this problem together and then enjoy another one. So we go a few pages back, right? There we go. So the F equation is the equation which you obtain from your word problem. The word problem will say maximize the volume. Okay, great. Volume of the box is x times y times z. Great. So F equals x, y, z, right? Or they will say maximize the volume for the box with a square base. Oh, okay. Square base, that's x squared y, right? Because if the base has the x and x dimensions, so that's x times the height would be y, so you would have something like this. And then say, subject to the, and they give you the unit circle as the shape. So that will be that line in xy plane. So now when we have the F equation and the G equation, we immediately go with the Lagrange multiplier. And Lagrange multiplier is when it's go del F equals to del lambda del G. Now, those of you interested in theory, you will take a look at the parallel gradients, and you will see that Lagrange multiplier is just a scaling factor, and you know it's fun. Once you write down Lagrange multiplier and take those partial derivatives, right, you get your gradients. The x component of the gradients are equal, the y are equal, the z are equal, and then you have the G equation as the additional equation to satisfy the amount of variables you have. And then, for that, from that point on, is the portion of the problem that we call good luck, right? So, whatever witchcraft you can come up with to solve that is fine. Just be careful that you are not dropping solutions, right? As I said, the reason why in this particular problem those points 1, 0, 0 and 0, 1, 0 clearly, negative 1, 0, 0, sorry, did not work is because this problem actually does have a volume word problem attached to it. And as soon as you have this structure of x squared y or xy squared, whatever, right, you immediately know, right, that you cannot have a side that will be 0, because you can't have a box if one of the dimensions is 0. So that's that. Let's see. Something for you to enjoy. What are we going to do? 8, 10, 12, 14?
I think 8.
You think 8?
I feel like that's like gonna be the second.
No, it's good. Just keep lowering the bar. So z equals f of xy is equal to, and now we have x squared plus y squared. With the constraint, oh, well, here we go. 2x squared plus 3xy plus 2y squared equals 7. Perfect. Have fun. By the way, that would be a cool tattoo. Wrong that.
And then plus 1, 2. Oh, so just 0. Yeah, not reverse. So what I did was I solved no, plus 4.
That's what I got.
And then lastly, you have this equation.
I was writing it square root.
So I still oh, I still can use these We got this so much so far. I don't know how we use this. But we solve for like here, right? But the only thing is, I got that like, why? Yeah, that's what he did on the first one. Now he gets 2x over 4x plus 2y. Now you use your definition.
Okay, let's take a look at this together. So I have my, so del f equals lambda del g. So vector of partial derivatives 2x and then 2y is equal to lambda. Over here I have 4x plus 3y, comma, 3x plus 4y. So I have first equation given as 2x is equal to lambda times 4x plus 3y. Then I have 2y is equal to lambda times 3x plus 4y. And finally, we have the equation 2x squared plus 3xy plus 2y squared is equal to 7. So 3 equations, 3 unknowns. I'm going to box these equations because this is important, right, to get there. And now we're supposed to solve this. Now, the best trick of all time for these nonlinear equations is if you have symmetry, x equals y. Now, how do we know that we have symmetry? Remember, if you swap x with y and y with x, you get the same equation back. So, if I am to swap each x with y and each y with x in the first equation, I would have 2y is equal to lambda 4y plus 3x. And that's exactly the same as the second equation, as you can see, right? So these equations, how many of you have gotten the equations that have x equals to y? Yeah, right? But yeah, you did a lot of work. That's fine, because you can drive to RVCC through Lincoln Tunnel. It's fine. All right? It just takes longer. So now I just gave you the teleportation method, so you don't have to go through Lincoln Tunnel, right? So if you have, right, guys, write this in blood on the side, right? Symmetry. Symmetry, x equals y. And then you just need to plug that x equals to y into the third equation and you are done. So if you have symmetry, it is going to be 2 or 3 lines of solution. Now, probably you have a whole page of blood, sweat, and tears, but that's okay, right? You learn, it's a learning experience. So now that I know that x is equal to y or y is equal to x, I will plug that in. And I will have 2x squared plus 3x squared plus 2x squared is equal to 7, for a total of 7x squared is equal to 7, from where x is equal to plus minus 1. Are we all there? Beautiful. Which immediately tells us that y is plus minus 1. Now, you will be tempted to say, oh, 4 points. Right? No. It's 2 points now. Why?
Do they go together?
Symmetry. So x equals y. Exactly. So you cannot have 1 and negative 1 and negative 1 and 1, right? You can only have 1, 1 and negative 1, negative 1. I know, right? That's okay, no problem. So, because of symmetry, this time around, we are only going to... So, guys, you better have 4 points, right? This is supposed to be 4 points. 1, 1, 1, negative 1, negative 1, 1, and negative 1, negative 1, right? That's 4 points. However, there is a condition that x must be equal to y. Therefore, those combinations of 1, negative 1 are scrapped. So, only 2 points to consider. Because of symmetry, and that will be 0.11 and negative 1, negative 1. Now, these are the 2 points that you will plug into your objective function, and they're both are going to give you the same value, right? They're both going to give you the same. Then you have to go and figure out whether it's a min or a max. So f of 1, 1 is going to be 2, and f of negative 1 is going to be 2. So you have 1, 1, 2, and negative 1, 2. So these are our max or min. Well, we have to figure out what these are. And there are ways in which you can figure this out. You can use the derivative if you want to. You can calculate the points next to it and see, right? Because for the maximum, right, the surrounding points should be lower. And for the minimum, surrounding points should be higher. So you can move along the circle line a little bit to the left, a little bit to the right, and compute the value. Yes?
Wouldn't it be the same because the equation is x squared plus y squared? Because even the negative would be positive?
Well, we did get the same, right?
Yeah, but like when you check the points next to it.
Yeah, but you just need to check one. That's why I said, you pick one to the left or to the right. Because it's a square and square, yes. So for the previous example where we have x, y squared, you would have to check, right, both sides. But in this case, just check one, right? You check one along the circle that it's close to.
Would you be plug in f 1, 1 get 2 to the original subject?
To the f equation, the objective equation, yes. Now, how tedious is this? Well, it's very tedious. You are going to move x or y to whatever position you want. And then, so move x. So let's move x to 1.1. When you move x to 1.1, you use equation g to calculate y, and then you use the y that you get from there with the x in f to calculate z. Woohoo! I know, it's awesome, right? So, guys, the point, you cannot just pick any x and y. You have to pick x and y that it's on g, right? Because that's your constraint. All of your points of input for f have to be on g, right? Because, one more time with a spray bottle, f is the spray bottle. G is the black line. Observe that the black line is on the spray bottle. So G is on F. So if I pick any random x value, I can't pick this x value because that's not on the object. But if I pick this x value, then I have to calculate that x value in the G equation first to make sure that for the selected x value, the y value is on the black line. And then I use, once I secure that the point is on the black line, then I can use function f to use that x and y to compute z. So we move our x to 1.1. We just move a little bit, right?
How do you know though that that's on G?
The 1.1?
1.1.
The domain of G is right over here. Yeah. So if you make educated guess, right? 1.1, because it's close.
How do you know you're wrong if you're wrong?
Because the equation is going to give you imaginary number, because you won't be able to compute y.
Okay.
Right.
So we can't choose 100.
Maybe you can. I don't know until we try. Right. You can actually go and use your very first lecture on functions in chapter 12 to figure out what the domain for f is, which would give you the region, right? In this case, this is some kind of a sideways ellipse. This is a slanted ellipse. That's what some kind. I don't know. Maybe not. Whatever this is, it's something. So, should be ellipse. So what I'm going to do is I'm going to pick any x, because if you look at the equation, you don't have any restrictions on x. You can pick 100, right? But 100 is really far from 1. So I want to use 1.1 because it's very close, right? So when I use 1.1, then I go to my g equation and plug that 1.1 for each x. So from the g equation I have 2 times 1.1 squared plus 3.3y plus 2y squared is equal to 7. And you see that you are getting a quadratic equation which is going to give you 2 values for y. Yeah, exactly what I need. 2 values for y. That makes sense. But we only compute 1 because when you square it, it's going to be the same, so who cares? All right, so let's go. This is going to be 2y squared plus 3.3y plus, this is going to be 1.21, so 2.42, and then minus 7 equals to 0. So 2y squared plus 3.3y minus 4.58 is equal to 0. And here's your quadratic. Now, if you end up with a value that it's imaginary, well, in that case, right, you have to figure out different, maybe 0.9, right, for x. You play with the values until you figure out what it is. So now you have this quadratic. The fastest way to deal with this is obviously to plug it into Wolfram alpha. You just say solve, and then you type in the equation. So that's going to be 2. I'll change it to, well, 2y squared plus 3.3y minus 4.58 equal to 0. And I'm going to, it gave me the full values, but I'm going to use the decimal. So it gives me the y is equal to negative 2.55 and y equals 0.90. So these are my y values. So now I have a point which is, I need to compute f, well, z, right? So z is equal to f computed at 1.1 comma negative 2.55, and that is going to give me z. So I have 1.1 squared plus negative 2.55 squared. So we use, well, the first one is easy, right? That's 1.21 plus 2.55, no, yeah, 2.55 squared is 6.5 is fine. So that's going to be 7.71. 7.71 is bigger, so these are min values. Good. Why work problems with 2 variables if we can have the ones with 3, right? Our equation can be done in any dimension because it's del f equal lambda del g. If you have 17 dimensions, you'll have 18 equations. It's not a problem. Didn't have any. So let's see something nice. For instance, 16 is nice. That's the almost the first problem that they give. So f of xyz is equal to xyz subject to x squared plus 2y squared plus 4z squared equals to 9. So there's your 4x4 case. Scroll up real quick, sure. So I picked x, I computed y using g, and then I computed z using f. And compared. Okay.
X equals
What's the project?
Possibly today.
You just chose a different equation for data. So there's three. That's the picture.
Oh, xy. This is yz, right? So yz. Okay. Thank you.
No, we substituted.
We substituted. I was able to isolate the y squared and the 4z squared to z.
Yeah.
Oh, I cancel z and
Do we all have the same equations?
Yeah.
So the only thing that I can do here is solve for lambda in each of the equations and then equal those and see if algebra will clear anything up. So from the first equation, lambda is equal to yz over 2x. And over here, lambda is equal to xz over 4y. And lambda is equal to xy over 8z. So that's these. And now set the pairs equal. So set these guys equal, let's say, and we can either set these or these, whatever. It doesn't matter which ones you set. How about you go first and second and first and third, whatever. So when you set them equal, you get that yz over 2x is the same as xz over 4y. Well, this drops first, get 2 there. So when you multiply 2, you get 2y squared z is equal to x squared z. And now remember the trick. You move everything to the same side and you factor what you can. So 2y squared z minus x squared z equals to 0. And you factor out z, and you get 2y minus x squared equal to 0. Now you have z equals 0. 2y squared, yes, please pay attention, it's right there. I know, right? It was so subtle. Smooth.
Like 0, like.
No, it's 0, yeah. Z equals 0. Sure.
Where'd you get the 2y squared z?
2y. When you cross multiply over here, right? This 2y and y z is 2y squared z, right?
So it would have worked out if we just dropped the variable. We would have just canceled the z out. It still would have worked out.
Now, if you cancel the z out, you will never have z equals 0 solution. You would miss it if you cancel.
Wait, so when you solve for lambda, you have 3 lambdas now.
We only did these are the red lambdas. That's the red lambdas. And then we're going to do the blue ones later. So we have these two equations now, z equals to 0 or this. So now if z is equal to 0, we can plug all of this in the on a third equation and solve and see what we get, right? So we have, instead of x squared, I write 2y. Y squared plus 2y squared, z is equal to 0 is equal to 9. So that's 4y squared is equal to 9. Y squared is equal to 9 over 4, from where y is plus minus 3/2. Nice. And if I have y squared, then x squared is equal to 2 times y squared, which is 9 over 4. These guys die. We just have 9 over 2. So x plus minus square root of this, which is 3 root 2 over 2. Right? The square root of 9 is 3. The square root of 2 is square root of 2. Rationalize. 9 square root.
Just follow up for a sec. So, like, what equation did you plug in on the 2y? Okay.
In the G.
And did you make the z 0?
Yes. So now we get 4 points over here, right, with z equals 0, and that's the first half. Then we have to do the blue one. So this most likely will have 8 points. So we have x is equal to 3 root 2 over 2, y is equal to 3/2, z is equal to 0. 3 root 2 over 2, negative 3/2, and 0. Negative 3 root 2 over 2, 3/2, 0, and negative 3 root 2 over 2, negative 3/2, and 0. Now guys, these are just the input points. What was the dimension for this problem? X, Y, Z. So is it Z something that we look for min and max? No, Z is one of the 3 inputs that we have. We are looking for W equals F of X, Y, Z. So now if we're gonna compute, well, luckily it's just X, Y, Z. So you just get to multiply these and you get 0 for each one of these. So yay, right? But
How do you know if there's not like more?
oh, there are. We didn't do the blue ones yet. Well, this is just for the red, right? Because when I solved each one of these equations for lambda, I only set this one equal to this one, which is the red, and everything that follows after that is from the red pair. Now you can either pair first and a third or second and a third, whatever makes you smile at night. Neither? Okay, fine. So we do the blue one then. So now we do the second half of the problem and the calculation when we equal yz over 2x to the lambda on the bottom, xy over 8z. No coffee. And that's the blue pairing. And now we do the same thing. So when we cross multiply over here, we get 8yz squared is equal to 2x squared y. The 8 and a 2 will cancel, and we'll get a 4 instead. Now 4yz squared minus x squared y equal to 0. Factor out y. Have your 4z squared minus x squared equal to 0. So y is equal to 0, or x squared equals to 4z squared. So now we plug that into the objective equation up there. So x squared is, so I'll go like this and say plug into g of x, y, z. So we start with 4z squared plus y is done plus z squared. No, it was 8z squared, right? Or 4. It was 4. Yeah, 4z squared equals to 9. So that's 8z squared equals to 9. Z squared is equal to 8 over 9. When you square root that, you get 2 root 2 over 3. No. It's 9 over 8. And then z equals, square root of this is 3. And then this square root will go up there with a negative sign. So that's 2 to the just 8 over 9. Which is, for a single z, 3, and then 2 root 2, and then root 2 is 3 root 2 over 4. And that's when we only use the first one. Now you, yeah, well, later. So what do I have? I have that the z squared, I have the z squared which plugs in there, which will give me what? See you next week. Eight over 9 there. It gives me x squared is equal to times 9 over 8, perfect. And that's going to be, these guys cancel, so that's 9 halves. So x would be 3 over root 2, which is 3 root 2 over 2. Perfect. So we have x, I have my y, I have my z, so 4 points again. So when x is, this is supposed to have a plus and minus in front. So when x is 3 root 2 over 2, y is 0, and z is 3 root 2 over 4. Then the same point with the minus. No, it's not a 0 at the end. It's x flipped. So minus 3 root 2 over 2. Good. Did you just say 4? Because it is 4. I was just testing you. Make sure that you're mentally present after all these calculations. The worst possible joke I can make now is like, a good thing I have to take the test. It's like, yeah. There you have it. Oh wait, I don't have the other two. 3 root 2 over 2, 0. 3 root 2 over 4, and this one needs to be negative, and both negative. What's fun here?
Nothing.
Word problems. That was premature. And immature. Maximizing a sum if you add 4 numbers to 16. No, maximize the value of the subject to condition, right? So maximize the sum. Here's the cool problem. The planes blah blah and blah blah intersect at a line L. Find the point on L nearest to the origin. Right? So you have two planes and they will intersect at a linear line, and you're supposed to find the closest point. Well, that's minimizing the distance point, right? So you have that. So there's a whole bunch of they only give you four problems. I'm not sure where the rest of the problems are. Differentiable function, whatever. Geometry, I find the maximum. Yeah, it's not too happy. Aha, there they are. These are the word problems. So they're really cool. I mean, in my opinion, obviously. You think whatever you want. There they are. So box with a minimum surface area, extreme distances, maximum area rectangle in an ellipse, maximum perimeter rectangle in an ellipse, minimum distance to a plane, and so on. So let's set up one of these to see the words versus the previous problems where you just have everything given. So what should we do? 30? Minimum distance to a plane. Find the point on the plane closest to the point blah blah blah. Great. So we have some kind of coordinate system x, y, z. In that system we have a plane, and then there is a point, and we are looking to get closest to the plane, so that will be stretching up to this point. So this is the xyz point unknown. We want to closest distance, so this is min, and the point, minimum distance plane to a point closest to the point, -2, 5, 1. So clearly your constraint G is given by the equation of the plane, because the point you're looking for must be on a plane. That's the constraint, right? This pen must be on the plane, right, which is the desk. So you have your constraint. So for this problem, constraint is 2x plus 3y plus 6z minus 10 equal to 0. And now for f. For f, we need a distance formula for f, because we are looking for the shortest distance between the point and the xyz that are unknown. So the shortest distance will be x plus 2 squared plus y minus 5 squared plus z minus 1 squared equals a minimum. So you have your f, you have your g. Del f equals lambda del g. Here's the Nike symbol. Let's go to lunch. So that's the word problem, right? The word problem. And you have a lot of these cool things. Look at the last one. The last one says, what's the largest, maximum cylinder in a sphere? Find the dimensions of the right cylinder of maximum volume that can be inscribed in a sphere of radius 16. Technically what you have is a sphere, is a ball, right? That is, it's like a bead for necklaces, right? So you have a ball, but then you have the opening on top, and you have the cylinder, right, like that, through the hole. So find the dimensions of the right circular cylinder of maximum volume. Volume for the cylinder needs to be max. So that's your F. And the sphere on the outside is your G. And that's x squared plus y squared plus z squared equals to 16 squared, because the radius is 16. So the sphere of the radius 16. So your equation is going to be x squared plus y squared plus z squared equals to 16 squared. And then you just grind through calculations like we just did. And definitely have fun with taking the square root of that square root, right? Taking the derivative of the square roots for the, right? And can you exploit the symmetry of that one? Nope. And nothing with 30-40 minutes of Sunday won't solve. It's a quick example, right? All right, well, that's that. Lagrange multipliers in all of their glory. Bye. Thursday exam will have chapter 12 on it. We can do some preliminary discussion and stuff. More same thing that you're expecting as in your exam 1. So about 10 problems. Clearly, 12.8 and 12.9, a little bit of a carpal tunnel developing. Right? So if you have any test-taking skills, you know that those problems are to be left to be done last, because they take a long time, and there is nothing worse than when you burn 30 or 40 minutes in the beginning of the exam solving Lagrange multiplier just to get the complex value at the end, and then you realize that you dropped the minus sign on the line 3, right? And then from scratch the entire page. That's not that bad when the rest, when the 70% of the test is done. But if the Lagrange problem is the first problem you're doing, and you burn half of your time on it, and it's wrong, well, yeah, you see how the stress and sadness settle in quickly. So the biggest test-taking skill for the next exam is to read the entire exam and fish out the Lagrange multiplier and min-max procedures, because those can be potentially long. If you remember your first exam, well, a whole bunch of you got it wrong. The normal vector took forever, I think, or whichever one. One of those took forever to compute. Really long time. Well, you see the Lagrange multiplier. Now, generally I keep Lagrange multiplier a 2-input variable, but you are still solving 3x3 nonlinear system, right? If I have 2 input, x and a y, toss in lambda, and that's your 3 equations. So you can have 3 equations at the minimum, right? And generally what we deal with in Calc 3 is 3 equations or 4 equations. So 2 input variables plus lambda, or 3 input variables plus lambda. What else? Directional derivative. Hopefully you will remember to make your unit vector, right? Because directional derivative is gradient times the unit vector. And I know in class I gave you the vector 3, 4 because I'm mean and evil. And then a whole bunch you had to erase later. Because you use 3, 4 instead of 3/5 and 4/5. Where 3/5 and 4/5 are unit vector because the magnitude is 1. And 3, 4 is not a unit vector, right? I think that's it. I can't recall anything else. About 10 problems, no bathroom, and no graphing calculators. And draw something nice in the back, so so I like you, right? And higher stakes on the next exam, right? The grade goes up to 13%, which is the reason why the first exam never matters at all in my class, whether it's a 0 or 19 or 50 or 100. It's technically all the same, right? Because even with a 0, you are still in that mix for A. Now, the next exam is 13%, and then the following is 16%. So, guys, the stakes are growing, right? As you are going through this, you might skip exam 3. I don't know. Then your final is 30 plus 16, 46%, which is what summer 1 Calc 3 did. And that was my first time when the calculus course skipped the exam in me offering this deal 3 years in a row. So,
I'm going to go for that.
Same. I mean, if you schedule your exam on Tuesday and then your final is, or Monday, and your final is just a few days after that, what's the difference? That was the argument to win. In class, one student posed that argument. He said, well, we are going to have exam on Monday, and then we're going to have a final exam on Thursday, and then technically whatever you know for Monday, you will know for Thursday, plus you have those extra 4 sections in chapter 14 that we must cover. If we can cover more, we will. So that was the winning argument. The student said it's a summer course, and we are going to have 2 exams, so why have 2 exams and spend that much time on exams where we can spend more time on the review and going through material slower and more lab and more everything. So I don't know, whatever. So far in 3 years, intermediate algebra skipped exam 4 twice, and Calculus 3 skipped the 3rd exam once. So that's only three exams. Right? Now, how many courses do I teach? I teach 5 in the regular semester and 4 in the in a summer. So that's 14 times 3. That's 52 courses. So in 52 courses that I'm offering this deal of no exams, only 3 times were that offer was taken. So there you go.